Welcome to a lesson with Dr. Powell. Let's look at an example where we're using a matrix to represent the equation of a conic section. And we're trying to figure out what conic section is this a rotation of, and what is that rotation angle? Okay, so first, um, we notice something that if we put this vector here and its transpose over here, this matrix right here is what you might call a bilinear form, like a vector input as a column on this side and a vector input as a row on this side. And when you multiply this out, think about what you're going to get. You're going to get a 1 by 1 because you have like one row here and one column there. And it's going to be just an expression. In fact, the expression that we get is actually going to be this one right here. Um, you can check that out. The only way that we can get an x squared term is from this position and y squared term from that position. And then here, you're going to get two things like an xy, and a yx if you work this out. You can try this out. In fact, let's just do that. This means literally x times the first column, y times the x times the first row, y times the second row. So you get 4x plus 5y, and we get 5x plus 4y. And then we do the same thing. Okay, so we did x times the first row right here, and then we said y times the second row. And then we added those together, and that's what we get right here. That's what this result is. Then we take that, we multiply it to xy, and then we end up getting 4x. So we get x times the first thing, 4x squared plus 5xy, then plus y times the second guy, 5xy plus 4y squared. Notice that we get this. So we can kind of basically what we do is we take this, we divide it in two to see the 5 and the 5, and this 4 we put there and there. Okay, so we can get this matrix from here. Now we're going to diagonalize this matrix, and we're going to orthogonally diagonalize it. Realize this is a symmetric matrix, which means that its eigenspaces are orthogonal to each other. So let's go ahead and diagonalize this matrix. We get x minus 4, x minus 4. So we have like x minus that matrix, minus 5, minus 5. Take the determinant, and we end up getting x minus 4 quantity squared, and then minus 25. So we get x squared minus 8x plus 16 minus 25, which looks like minus 9, x squared minus 8x minus 9. So we have x, and we have a, let's see, minus 9 and a plus 1. Okay, so we have two eigenvalues. And we can think about those eigenvalues right here. So we get two eigenvalues, 9 and 1. So that's going to be our diagonal matrix. We can write 9 and 1 right here. And realize that this x that I'm using, maybe I could have used a lambda or something. This x has nothing to do with that x over there or in the equation. It was just, it was representing the actual matrix right here. So sometimes we use other letters here. Maybe we could have used a Greek letter, lambda, like I was mentioning. That's common for that case. Okay, but nonetheless, we get, so not to confuse it with that. So this x has nothing to do with that x. This is simply the scalar that's representing the matrix. Okay, so we get 9, 1, 0, 0 as our diagonal. And then over here, our matrix that diagonalizes, we need to get some eigenvectors. So we have x minus 9. So we think of the matrix minus 9. That would give us down the diagonal a minus 5, a minus 5, 5, 5. The x plus 1, so you add 1 down the diagonal, you'd end up getting 5, 5, 5, 5. Notice from here, I think a basis for this range is 1, 1. And then if we, and then what we're going to do is we're going to divide it by its length. So we think a basis for this guy is 1, 1, and then we're going to divide it by its length. Its length is done just by the dot product of itself and square root that. So 1 squared plus 1 squared is 2, and then you square root that. So that's the length. So we're literally taking this vector and then dividing out. And we do the same thing over here. So we have negative 1 over root 2 and 1 over root 2. So this is actually the eigenvector for that, and that's actually an eigenvector for that crosswise. So what we have, if we have 9 as the first one, we have a corresponding eigenvector right here, 1 over root 2, 1 over root 2, and then for, actually that's supposed to be a negative 1, sorry. We have two eigenvalues, 9 and negative 1, okay, because that's what makes that 0. Excuse me on that one. Okay, and then for the x plus 1, the eigenvalue of negative 1, we use that guy, negative 1 over root 2, 1 over root 2. So this is so that's our matrix right here that we multiply on this side by, and then we multiply by its inverse, which is nice for a matrix that's has an orthonormal basis in here, and it's orthogonal to itself right there, because you just take the transpose to get the inverse. And orthogonally diagonalizing is nice that way. So we've diagonalized it. Now look at this matrix right here. What rotation is it? Well, let's think. 1, 0 is sent to, so 1, 0 is sent to this guy right there. So it looks like we've gone by force, right? And let's see. And you can even, look at this one. So 1, 0 has gone to this location, which is over here, which is, yeah. So looks like we've rotated by positive pi force. Okay, so we see a positive pi force, and that's actually exactly what's been done. As we think about it, when we go from, so we started out or thinking about this matrix right here, 9, 0, 0, negative 1, which if this was replacing this guy up here, this would look really nice, 9x squared minus y squared. So a rotation is equal to 9. A rotation's been done from here to get us to here. And the rotation that's been done to go from here to here actually is a positive pi force angle. If you were to graph this guy right here, it looks something like this. And then pi force actually rotates it just like that, going that way, like that. Thanks for watching.